So there's this formula that shows up a lot, particularly in the analytical chemistry lab, and it's something I think kind of needs a video to kind of explain the nuances with it. I had a really good calculus instructor say that if somebody can't explain the math to you, they don't understand the math. And I think that's a very, very good way of looking at it. So this comes about from calibration curves, and it's going to use a lot of the terms that are found in your line S equation. But I want to talk about, because I had a student ask me one time about a GC lab, and the gas chromatography lab. Their standard deviation was, their S from this was huge, and it was like, I don't understand, my calibration curve looks really good. It's like, your calibration curve does look really good. The problem is that you're sitting on the edge of your calibration curve, and this is what the S is telling you, is that you're not really capturing that. You're kind of into areas of uncertainty in your calibration curve. So let's say we have a calibration curve, and we're going to throw data, and this isn't terrible, but let's pretend that it's actually linear. So what is the uncertainty here telling you? Well, your S of R term here is basically measuring uncertainty in the fit. So basically when we do this linear regression, how much does the linear regression kind of get away from the line of best fit? Basically it's reflecting kind of the random error within your data set. And so what we expect is that as S of R increases, we expect the uncertainty to increase. So the more randomness you have about the line, the more you expect your uncertainty to grow. Now in here is the number of unknown measurements, in here is the number of known calibration measurements. Now I do disagree with a lot of lab manuals. I see a lot of lab manuals kind of telling you to repeat standard calibrations over and over again. I think that's what's called gaming your p-value. So if you create 5 standards and you measure them twice, is M here 5 or 10? And I would argue that it's 5, not 10. Why? Well, the M here all have to be independent. If you've measured the same data point twice, you haven't really captured more of the curve. You just measured the same curve twice. So you're getting a better feel for the uncertainty of the fit. You're getting a better feel for the random noise in the Y measurement. But you don't truly have independent data points. And again, we're going to kind of illustrate this with what we're doing here. But some people do say that you can turn around and take the standards and measure them twice, and that doubles kind of like your N for your measurements. I disagree with this because by that line of reasoning, I should be able to measure a blank in some point 5 times, and that's the equivalent of doing 10 standards. And if you're like, that doesn't make sense, that's kind of the school of thought I'm in. But you're also going to find with this, there's different schools of thought. So anyway, your M and your SM terms here are going to basically kind of reflect the uncertainty, and typically when we're doing these types of calibration curves, we're mostly just dividing by slope. We typically ignore the y-intercept, especially with Beer's law calibrations. So this is a conversion factor here to kind of get you back to the uncertainty in x. So that's why this term here is kind of reflect the fact that, yeah, we're not looking at y directly, we're having to convert y to x, and that's what that's doing. The important part, though, is this part here. So the y bar here is the average in your unknown, and it's the average in your calibration set. So whatever the y range is, or the average y. And your y here is whatever your average value for the unknown is. So if you had more than one unknown measurement, what was the average value? Why does that matter? Why is that a factor in this? Well, consider your calibration curve. And we'll consider this data point here. How do we know that the line is linear through there? Well, we actually have a lot of data points to back that up. If we consider these two, we start looking at all the different combinations around it where we can fit a line through it. We start getting really confident that it's a line through there, because not only are the 2 most adjacent points sitting on a straight line, the ones beyond that are also sitting on the straight line. The ones beyond that are also sitting on the straight line, and so forth. So we expect the uncertainty to get better as we get towards the center of our calibration curve, because that's the point we have the most data points around. We're very confident that it's a line through the center of the data set because we have points above and below it. But let's say we start getting to the extremes now here. Well, yeah, we can draw a bunch of lines, but we're kind of relying on this last point here to anchor us in place, to show us where that line ends. We're constantly relying on the same point. Whereas here, we can pick multiple ones for endpoints. Same thing's true down here, is that if we consider a data point that's measured down here, and our blank is the only thing we have left, that blank is doing a lot of work to kind of show that it's a line. And what you'll see is the lines fluctuate around y. So what actually happens to S, your standard deviation, or your expected standard deviation off the plot is that it's going to get worse as you get towards the edges of your calibration curve. And this is by merely the fact that we are less certain it's aligned. So consider it up here. For all we know, it does this, it does this, it does this. We don't know, it looks pretty linear up to that point, but we could be wrong. Now you can turn around and say, well, down here we know it's 0, we can't get negative. Here's the thing, your stats tests don't know that. We don't know where you measured in your calibration curve. For all we know, you ignore the 0. But it's going to have to make the same assumptions that down here we don't know what the curve does. The more we are in the center of a linear function, the more confident we are that function is linear. But as we start getting towards the edges, we expect our uncertainties to get bigger by merely the fact that we're just not as confident where we're measuring. So this is a big, nasty formula. A lot of it's just unit conversions. This, again, is just a unit conversion, converting that to the uncertainty in x. But again, there is a big reason for this, is that it's kind of reflecting, one, the uncertainty in the fit itself, as well as where you're measuring at within the curve, versus how much you use to build up that curve, versus how much you actually use to build up your unknowns. So again, I know it's a big nasty formula. I hate entering in Excel every single time I have to do it, but it is like there is a reasoning behind it. There is an intuition behind why the uncertainties grow the way they do.